So, welcome all of you for the current lecture on gravitation. So, this is a good time for us to recollect all that we have done so far. What we did was to first start with estimation of distances of astronomical bodies from the earth. Prior to that, actually, we also looked at how to estimate the radius of the earth. Assuming that it is perfectly spherical, otherwise what you are going to get is the mean radius. Then of course, we went on to discuss trigonometric methods for estimating the sizes of the moon, the sun and the planets. These required extensive and careful observations of the orbits of the moon, the sun and the planets around the earth over many centuries, and by using simple plane trigonometry we saw that all these could be estimated. And then what we did was to enumerate the planetary laws of motion. Planetary laws of motion, which is due to Kepler. So, these laws of motion are very important for us, because there was a shift in the frame of reference, whereas earlier everyone tried to find out or discover the systematics and the planetary orbits by looking at it from the earth frame of reference. Kepler shifted from the earth centered frame heliocentric frame. Kepler shifted from the earth centered frame to the heliocentric frame, and there he got an excellent fitting with elliptic orbits, and he was able to enumerate the three laws. So, if you remember, the first law said that the orbits were all elliptical. The second law said that the planets sweep equal areas in equal intervals of time, and the third law related the period of the orbiting planet to the distance from the sun. T squared over r cubed was a constant, and these came as a great surprise. So, at this point we should remember that in India also there was the Kerala School of Astronomy, who actually found that the algorithms for planetary orbits could be much simplified if one assumed the frame of reference which was fixed in the sun. Today it is a well established fact, but anyway, leaving that part of the history aside, what we shall do is to continue with our revision. So, these are the three laws that Kepler obtained, and to supplement it with dynamics, because we want a theory of gravity, we also discussed Galilean law of falling bodies. Galilean law of falling bodies. This law is very important for us because, philosophically speaking, although it may not matter much to us at this time, it went against the Aristotelian paradigm that lighter objects go upward, heavier objects come downwards, or to put it a little bit more quantitatively, heavier objects fall faster than the lighter objects in the gravitational field of the earth. But Galileo did fairly careful experiments from the Leaning Tower of Pisa. So, he dropped two objects of two different masses. He was intelligent enough to choose them such that the viscosity of the air, the lift of the air is not very important. If you throw a piece of paper, then of course it will not fall as given by the law of falling body. Its g will not be given by 10 meter per second squared or whatever. He did that, and we found that the acceleration is independent of the mass of the falling body. So, we write ma equal to mg, and we cancel and we get a equal to g. This equation that I have written here, ma equal to mg, also brings out another very fundamental fact or fundamental principle of physics, namely that inertial mass is indistinguishable from gravitational mass. So, we write mi equal to mg, and that is how I was able to cancel. And we had a fairly long discussion on this fact that mi equal to mg. This is what is known as equivalence principle in physics, and this is the bedrock of Einstein's general theory of relativity. We give up many things, but we do not give up mi equal to mg. So, whatever I have listed so far formed the basis for Newton's formulation of law of gravitation. So, Newton looked at the Galilean law of freely falling bodies, Galilean law of freely falling bodies, orbit of moon around the earth, orbit of the moon around the earth, orbits of planets around the sun. So, this was the information that Newton had, and out of this he had to build a coherent theory. All these were facts, and the understanding was empirical. There was no theoretical basis, but Newton provided a theoretical basis by using all these to formulate universal law of gravitation. This was the first universal law, the fundamental force to be discovered in physics. And even today, it is an extraordinarily fascinating interaction. We do not completely understand that. So, all of us know what the formulation of universal law of gravitation is. The most important thing is that it is an inverse square law, and then there is a constant which characterizes the strength of the gravitation, and that is the Newton's gravitational constant. So, how do we write that? If you have a body of mass m1, if you have a body of mass m2, so let us say we ignore their sizes, so treat them as point masses, and then if they are separated by a distance r, so what did we say? We said that my force experienced by 2 because of 1. So, 1 is acting on 2. So, that is what we wrote, was simply given by g m1 m2 by r squared. So, if I denote the unit vector r from m1 to m2, this will be directed towards m1, therefore, I put r. That is what I am going to do. In a similar manner, by making use of the third law, the force experienced by mass m1 because of m2. So, how are we going to write? 2 acts on 1. So, this is a good notation which causes no confusion. This is nothing but minus of f1 comma 2. This is what we have. So, if we did that, the only unknown quantity would be the universal constant, this gravitational universal constant of gravitation, and we also discussed how Cavendish in his beautiful experiments was actually able to measure this g. So, the value we owe to Cavendish. And I gave a fairly long description of how Cavendish was able to do his experiment in a barn, trying to protect it from vibrations, etc., and he got a fairly good number. Please go back and listen to that and revise this part. Cavendish, of course, did not call it as the determination of the gravitational constant, but he called it as weighing the mass of the earth, finding the mass of this earth, because this g is related to the mass of the earth through the acceleration due to gravity given by the Galilean law of falling body. So, that was a very great accomplishment, because we cannot have ordinary balances in order to measure the masses, but Cavendish was able to do that. So, essentially once you have gravitational law, you can determine the masses of many objects. I discussed that also. I told you how the sun can be weighed because of once we know g. So, it is a great accomplishment of the theory of gravitation. So much so, people thought that we have the key to almost all the secrets of nature, perhaps all the secrets of nature. So, there is a very famous poem due to Alexander Pope, who wrote that nature and nature's laws lay hid in night. God said, let Newton be, and there was light. So, it was Newton who threw light on nature and her mysteries. Now, all this has been a spectacular thing. So, what we are going to do today, as I discussed at the end of my last lecture, is to show one very important application of the law of gravitation, and that is phenomena of tides. So, all of us who have visited the seashore and spent some days, and all of us who stay by the seaside, we know that the height to which the water level rises or falls shows a regular pattern depending on the day, depending on the time of the day, and also depending on the phase of the moon. It is of course intimately related to the phase of the moon, because the tides are the most spectacular on the full moon night and the new moon night. There is a great difference between what happens during the daytime and what happens during the night time. And in almost all societies, the moon has been associated with the mind and all kinds of powers. So, for a long time people believed that the occurrence of tides was actually a supernatural phenomena, a manifestation of the great power of the gods. Well, it is indeed a manifestation of the great power, but not of the gods, but of nature, if you replace the word of gods by nature. And one of the important consequences or important applications of Newton's law of gravitation is that it allows us to quantitatively understand tides. In this lecture, I am not going to tell you all about the quantitative nature, because to do that would require lot more mathematical work and lot more information. We have to know, for example, the compressibility of water, so on and so forth. So, it will be necessarily qualitative. But I would also like to tell you that the other important thing that the phenomena of tides from the viewpoint of gravitation is that many times it is not the magnitude of the force that matters, but it is the difference at two different points that matters. So, tides are very peculiar in the sense they are not sensitive to the magnitude of the force, but they are sensitive to the difference in the forces. And this gives rise to very interesting and surprising consequence, and that is worth learning. Interestingly, this kind of sensitivity to difference in gravitational force at two different points actually becomes very important in general theory of relativity. So, I would like to go back to that and give you an idea of what happens when you look at the tidal forces after describing the tides themselves. So, let us start to get working on the tidal forces. So, symbolically I am going to write Earth as a very, very big sphere. So, the Earth is treated as a sphere of radius Re. The Moon, as we know, is much closer to the Earth than the Sun. So, let us say my Moon, which is a small object, that is how we see on the sky. So, is seated here, and let us say the Sun, which is far, far away, is here. Without any prejudice, we are putting the Sun at some other point. That is what we have. The Moon has a mass which I will write mm. So, I will write Moon here. The Sun has a mass ms. The distance between the Moon and the Earth I denote by dm, and the distance between the Sun and the Earth I denote by ds. When I say that I am looking at the distance between the Sun and the Earth, what am I doing? I am looking at the distance between the center of the Earth with the Sun. We are not worried about the size of the Sun because the Sun is far, far away. But if I move along the surface of the Earth, we see that the distance changes from dm minus Re to dm plus Re. In a similar manner, ds plus Re to ds minus Re. So, there is a variation in the distance. Because of this variation in the distance, there is going to be a variation in the force. So, what are we saying? For any point on the surface of the Earth, the true distance varies between d sm plus or minus Re. That is what it is. Of course, the distances dm and ds are much, much larger than the radius of the Earth. So, it might appear that for all practical purposes, this is of no consequence. Like for example, when we look at the Galilean law of falling bodies, you may drop it from a height of 10 meters, you may drop it from a height of 20 meters, or even let us say 100 meters, you wouldn't care because the radius of the Earth is about 6,400 kilometers. So, we are speaking of 6.4 into 10 to the power of 5 meters. So, you say 10 meter, 20 meter, 30 meter is of no consequence, and that is the reason why we use small g, the acceleration due to gravity, without committing much error. In a similar manner, if you are to look at the radius of the Earth and the distance between the Moon and the Sun, it might appear to be a small correction. But as I told you, when we are looking at the difference in the forces, this is of quite significance, large significance, and that is what we want to understand. So, what I will do is to start with the Moon, Earth force. And then I will look at the Sun Earth force. Normally, when we look at the Earth Moon system, we always speak the language of the force exerted by the Earth on the Moon, because the Moon is in an orbit and the Earth is very, very heavy. So, at some point you will learn that both the Earth and the Moon are moving around their common center of mass, but then the Earth is so heavy the center of mass is practically in the rest frame of the Earth. That is exactly what we do in the case of Earth-Sun system. It is practically in the Sun. In your hydrogen atom, for all practical purposes, the electron is moving around the proton. That is what we do. But here, we are not interested in that. We are actually interested in the force exerted by Moon on the Earth. So, there is a shift in our emphasis. So, we are interested in the force exerted by the Moon on the Earth. Now, when I am making this statement, this makes sense if I also remember that a large surface of the Earth I think 2/3, if I remember correctly, a large part of the surface of the Earth is covered by water. Otherwise, for us, the Earth is a rigid object. Therefore, the difference between the force on different points on the surface of the Earth would not matter, because it is a rigid body. The distance between different the various points are fixed. But the water that we are looking at is not rigid. It is going to respond to the forces. It is a fluid. Therefore, we are interested in the gravitational force of the Moon acting on the water part of the Earth. So, we are interested in the gravitational force acting on water. Now, you see how it naturally connects to the concept of a tide. That is something that we have to understand. So, now let us look at what is going to happen. I am going to draw the figure again, quite exaggerated. So, there is this small point which represents the Moon. So, as I told you, this is my radius of the Earth, and this is dm, distance between the Moon and the Earth. I am going to plug in all the values, numerical values of the radius and the distances and the masses at the end of the calculation. But right now, what we shall do is to find the difference between the force acting at this point and the force acting at this point. So, I will call it as F1, and this I will call it as F1 prime. That is what I will call this. So, the Moon is exerting a force at this point, the Moon is exerting a force at diametrically the opposite point. It is attractive force at both the points, and the force of attraction at this point, the closest point, is larger than the force of attraction at this point, because the fact that this is farther away from the Moon. So, we have to write down the distances. So, what are we going to write? My F1, I am only going to write down the magnitude. We will not worry about the signs. We know that it is attractive. Is simply given by G me, the mass of the Moon, divided by dm minus re whole squared. That is what we have. In a similar manner, if I were to write the force F1 prime, prime is at the farthest point, what would be the force now? That would again be G me mm over dm plus re whole squared. What would happen if it were the Sun and not the Moon? Well, the mass of the Moon would be replaced by the mass of the Sun. The distance of the Sun from the Earth, ds, would replace my dm. So, that is what I would have, and we are going to use it in the next step. So, I am going to repeat whatever you people are thoroughly familiar with. the magnitude of the force keeps on increasing when the mass increases. Mass of what? I am interested in the force of the earth, on the earth. So if I look at the sun is much heavier than the moon, therefore it tends to increase the force on the earth. But on the other hand, if I look at the distances, the sun is much farther away, therefore the inverse square law tells me it tends to suppress the force. So what we are interested here is in the interplay between the computation between the masses and the distances. Larger mass but larger distance, smaller mass but shorter distance. So we are interested in that, and we are interested to see how it manifests when I look at the distance between the two forces. I am interested in these forces. So what I am interested actually is in delta F1, which is F1 minus F1 prime. This is what I am interested in at two different points, two diametrically opposite points on the surface of the earth, which are collinear with the location of the moon. That is what I am interested in. When I am doing this calculation, I would like you people to remember that D is much greater than RE. D is much greater than RE. Distance between the earth and the moon is of the order of 10 to the power of 5 kilometers. Okay, and here we are speaking of 6400 kilometers. So, and the sun of course is much farther away. So what are we going to do? In doing these calculations, we make a binomial expansion. So this is always the trick whenever you have a small correction to a large number. So let me rewrite that again. My F1 is given by some constant k divided by dm minus Re whole square, where k is gravitational constant, mass of the earth and mass of the moon. We are interested in the moon at this point. So what do? I first obtain the mean force and then obtain the correction. The mean force is what is acting at the center of the earth. That is what I have. Therefore I will write k over dm squared into 1 minus Re by dm whole squared. That is what I have. So we are saying that Re over dm much less than 1. This approximation is important for our understanding, and eventually we are going to substantiate this claim by putting in the values. So let me open it up. So this I will write F naught k over dm squared, everything is fixed in this, and I will write this as 1 over 1 minus 2 Re by dm minus Re squared over dm squared. That is what I am going to write. Ra by dm is a small quantity. Re squared by dm squared is an even smaller quantity. So 2 Re by dm minus Re squared by dm squared is a small correction to 1. So let us write this as F naught over 1 over 1 minus x. That is what we are going to write. So when x is very small compared to 1, we know how to make a Taylor expansion or a binomial expansion. Re by dm is certainly greater than Re squared by dm squared. X is a positive quantity, that is what I have. So I will write 1 over 1 minus x is 1 plus x squared plus higher order terms. You may wonder why I kept the quadratic term and did not just stop as x. because after all I have been asserting that x is a very small number. The answer to that is that I am looking at the difference between the forces, and that will manifest only at the level of x squared. This is the lowest order term that will contribute to the difference of the forces, whereas here there is going to be a cancellation when I subtract. So what is my x? My x is given by 2Re by dm minus Re squared by dm squared is what I have. So perhaps I should introduce a notation Re by dm. If I denote it as my small r, so this quantity is nothing but it is a ratio 2r minus r squared whole square. This is what I have. So what is it going to be? Sorry, there is no square here. 2r minus r squared. X squared will obtain the term. Now I want to evaluate x squared. So 1 plus x squared. So 1 plus 2r minus r squared is what I am going to get. And x squared is going to be 2r minus r squared whole squared plus higher order terms. Why do I keep this term? Because if I want to keep this r square term, then there is a contribution to r square term coming from this also. Otherwise, I would have to keep only the linear term r. So x is a small quantity, but that itself is a linear combination of a term which is linear in r and quadratic in r. So if I want to keep a term which is quadratic in r in the linear term in x, I have to necessarily keep the quadratic term in x squared, because I have to collect coefficients of all powers consistently. That is what I have to do. So what am I going to get? I am going to get 1 plus 2r minus r squared. Now you see, the first term is going to be 4r squared, and all the other terms are of higher order. Therefore, I am only going to keep 4r squared, and I will write terms of the order r cubed, etc. Because the cross term will be of the order r cubed, and the direct term will be of the order r to the power of 4, which I am going to ignore. Therefore, what I am going to get is essentially 1 plus 2r plus 3r squared. This is what I have. This is always the principle of expansion. We should consistently keep terms of a given order by looking at contributions coming from every other term. Notionally, x squared appears to be of a higher order compared to x, but actually it is not, because x itself is a combination of a linear term in r and a quadratic term in r. That is what I have. So now we are doing fairly well. I have to write my force here. My F1 is therefore given by F0. Dimensionally there is no problem about it. And then I have 1 plus 2r plus 3r squared plus higher order terms. This is what we are going to get. I hope that I have done all the numerical parts correctly. It is very important. Please verify that. Now what happens to F1 prime? My F1 prime is k, whatever that GMME is, divided by, what am I going to write? I am going to write dm plus re whole square. So let me do it. Let us not be impatient. This is what my force is. This quantity is k over dm squared into 1 over 1 plus re by dm whole squared. This is what I have. So my identification of x is different. So ideally speaking, in terms of my notation, I should write k over dm squared into 1 over 1 plus r whole squared. That is the correct thing to do. Because I denoted Re by Rm. This is capital R. This is my capital R. Re by Rm to be small r. Now I can compare it to this expression. This was the earlier expression came with a minus r. This comes with a plus r. Therefore, I get my f1 prime by simply replacing r by minus r everywhere in this expression. That is what I should do. So let me collect that. My f1 is given by f0 into 1 plus 2r plus 3r squared is what I am going to get, and my f1 prime is going to be f0 into 1 minus 2r plus 3r squared. That is what I am going to get. So I am afraid that I made an incorrect statement. I was under the impression that I would get a correction from the quadratic term. It is just the opposite. It is the linear term that is going to contribute. So anyway, because when you do the subtraction, please notice the quadratic term does not contribute. It was some kind of a lapse, but never mind about that. So my delta f1 is simply given by 4 f0 r, and my r is simply given by Re by dm. R is a dimensionless quantity. So we unnecessarily kept a term which is of higher order. I need not have done that. There was a momentary lapse, but it does not matter. So your delta f1 is simply given by 4 f0 Re by dm. Now I can find out in a similar manner what my delta f2 is. So what would delta f2 be? This would come from the force on the earth due to the sun at diametrically opposite points. Opposite points, collinear with the sun. So what is the geometry that we have? The geometry that we have is this is the sun, radius Re, moon, sorry, the earth, radius Re, this is the sun, and I have my distance ds. So by the same token, my delta f2 will be given by 4 f0 prime, because the distance from the moon to the earth will be replaced by the distance from the sun to the earth, and I am going to get Re over ds. This is the correction that I am going to get. So let me write everything in full detail now. Delta f1 is given by 4 g mass of the earth, mass of the moon divided by dm squared into Re by dm. This is what we are going to get, and delta f2 is given by 4g me ms ds squared Re by ds. It is a very simple exercise that you people have to perform. To check that, if you look at this point and if you put the moon somewhere here, the force exerted by the sun at this point is much larger than the force exerted by the moon. Obviously, we always worry about the motion of the earth around the sun and not the earth around the moon. Now, if you come to the opposite point also, diametrically opposite point, the force exerted by the sun at this point far exceeds the force exerted by the moon. The question that we are asking is, how does the force of the sun vary when I move from this point to this point? How does the force of the moon vary when I move from this point to this point? In other words, we are asking, how homogeneous is the force or the gravitational field produced by the sun? How homogeneous is the gravitational field produced by the moon? That is what we are asking, because we are looking at the difference. Now, the force by the sun can be very large. If it is homogeneous, the difference would be equal to 0. The force produced by the moon may be small, but if it is inhomogeneous, that difference can be large. Therefore, while the absolute values of the forces can be larger, there is per se no reason to assume that delta F1 is smaller than delta F2. F1 is smaller than F2 does not mean that delta F1 is smaller than delta F2, and that is exactly what we are interested in. So, what do we do? In order to appreciate that, we calculate the ratio, because we want to get rid of all the unwanted factors. I am going to look at the ratio delta F1 over delta F2. Please remember, the numerator is due to the moon, the denominator is due to the sun. That is what I am interested in. So, if I did that, whole lot of things will get cancelled, and what I am going to get is, this will be mass of the moon divided by mass of the sun. That is what I am going to get. RE will cancel, then I am going to get ds by dm whole cubed. That is what I am going to get. So, because the force due to the moon comes as dm cubed, the force to the sun comes as ds cubed. So, this is what I am going to get. All the other fellows will cancel. This is exactly what we have. So, as I was telling you, there is a competition between the ratio of the masses of the moon and the sun and the ratio of the distances between the sun and the moon. We have to worry, and there is a cubic factor which is there, which can actually upset the situation. We have to be aware of that. Now, this is the right time for us to plug in the numbers. Clearly, it is quite independent of the radius of the earth. It is quite independent of also the mass of the earth or gravitational constant. Now, I will start plugging in numbers, which I have noted down here. So, let me start writing this. Mass of the moon is 7.3 into 10 to the power of 22 kgs. Mass of the sun is 2 into 10 to the power of 30 kgs. So, you see, sun is really heavy compared to the moon. A million times actually, almost a million times is what we have. So, this ratio favors that delta F1 should be smaller than delta F2. But now, let us look at the distances. Distance of the sun is 150 into 10 to the power of 6 kilometers. I hope I have written it correctly. And distance of the moon from the earth is 0.3 into 10 to the power of 6 kilometers. So, what do? You take the ratio, this 10 to the power of 6 cancels, you are dividing 150 by 0.3, So 1500 into 3 by 10 is what you are going to do, divided by 10, whatever you are going to get that number. Then you are going to look at the ratio 7.3 and 7.2 with this factor of 10 to the power of this one. Ultimately, if you were to calculate the ratio, you will find, I am not going to work that out, the ratio turns out to be, this quantity turns out to be something like 3.5. I hope that this calculation is correct. Therefore, the difference in the gravitational force produced by the moon at the two ends is much, much larger than the difference in the gravitational force produced by the sun. It is of the order of 3.54, let us say. So what we can do at the first starting point is to ignore the sun and then ask what happens. I have the earth here, I have my moon here, and let us say it is covered by water. So there is a inhomogeneity in the force, gravitational force produced by the moon, and that delta F1 is there, which we have not calculated, but you can calculate that. So what happens, because there is a greater force of attraction and water is a fluid, water would like to move in this particular direction. Of course, there are forces of reaction and there is an increase in the height and there is a corresponding decrease here. That is what is going to happen. The sun is also going to do that. Therefore, an interesting question is what happens when I look at the period of tides at different points of the on different days of a given fortnight. That is what we are interested in. So what we shall do is to therefore look at a few scenarios, and the most interesting scenario is the new moon phase. So in the new moon phase, the moon and the sun are on the same side of the earth. That is what we have. Both of them cooperate. Tides are strong. In the full moon phase, the moon is here, and if you look at somewhere in the middle of the fortnight, on the 8th day, let us say a quarter, the moon will be somewhere here. Now the forces partially cancel. So essentially what happens is that depending on the day and the night, obviously because the sun is moving, is that okay? The forces are going to change, and correspondingly there is going to be an increase in the height, there is going to be a decrease in the tide. Of course, during the daytime, the sun and the moon, or in the night time, the sun and the moon are together, because I am never able to see the moon because it is completely blocked. What we see is the real high tide, is that okay? And this qualitatively explains what happens when the sun and the moon are at different phases. And this was the great explanation given by Newton. In fact, Newton did not bother to work it out. It was probably one of his students who did this, and this takes away the need to have the so-called super natural explanations for the phenomena of tides. So this is one of the important things. What we have to now do is to move on to a different topic, which is at the basis of the analysis of a whole lot of applications, and that is the concept of gravitational energy, potential energy. So let us recall what is going to happen. So imagine that you have a floor, there is a spring, there is a mass, and this spring is compressed. This spring is compressed and held by a stop here. This is a stop. Now what happens, as soon as the stop is removed, the block moves. The block moves. As soon as the block moves, that means it acquires energy. So, a good question to ask is, where did it get the energy from? Our experience tells us that this energy came from the fact that I did some work in order to compress the spring. My muscles got exerted, let us say there was a spring and I pushed it, and then I put a heavy stop. I did the work. So, I can account for the energy, my kinetic energy, whatever I pushed it, I did some work, to the kinetic energy of my muscular energy, I should not use the word kinetic energy, to the kinetic energy of the block. But then where did the energy get stored in the intermediate process? That is the question that we are asking. All of you know the answer to that from Hooke's law. Whenever you disturb the spring from its equilibrium position, so you moved in this direction, then there is a force F is equal to minus kx. There is a force that is a restoring force, and this restoring force wants to move the block away in this direction and you are stopping it. Therefore, this corresponds to a stored energy of half kx squared. This is the stored energy. So, if this block is oscillating about its equilibrium position, let me call it as x, small x is the displacement. At capital X, there is no stored energy. The force is 0, all its energy is completely kinetic. Then when it is oscillating, let us say it comes here and it comes here. These are the two endpoints of oscillation. At this point, there is no kinetic energy at this point P. It is completely stored energy, it is all potential energy. And similarly, in the completely compressed position, it is all potential energy. So, there is a continuous exchange between what is stored as a potential and what is manifest as the kinetic, half mv squared and kx squared, and the interplay between them is such that the total energy is always a conserved quantity, and that is the energy that I supplied. If I assume there was 0 energy at this particular point when it was at rest, that is what we do. Therefore, we write my E total is nothing but half mv squared plus half kx squared equal to constant. Now, one way of appreciating that, which all of you know, is to actually use this to obtain the law of motion. What do you do? If it is indeed a constant, then dE by dt must be equal to 0. It is a constant of motion. And this tells me mv dV by dt plus kx into v equal to 0. I have differentiated x squared, 2x dx by dt, cancel v on both the sides, and lo and behold, you get the Hooke's law, m dV by dt equal to minus kx. Of course, if you integrated this expression, you would get this. If you differentiated this expression, you would get this. Now, this is not that is something peculiar to springs. It should be peculiar to all forces, because Newton says in his law of gravitation that all forces behave in the same fashion. Now, I can imagine that I did exactly the same thing in the case of gravitation also. I picked up a ball, I did a lot of work, lifted my hand and I placed it there on a shelf or some such thing, and when I dropped it, the ball fell down. That is what I would like to say. So, I can again ask the same question, where was the energy stored? Because as soon as the ball hit the earth, by Galilean law, it has acquired a lot of velocity. So, this gives to the question of, gives rise to the concept of gravitational potential energy. I guess we shall discuss that in the next lecture, and I will use that to discuss escape velocities and launching of satellites, so on and so forth. So, but that we shall postpone for the next lecture. So, please revise these topics before you come for the next class. Thank you. Have a good day.